Good day everyone, I am Francis Annes Discay from BSPCE 3B, and today I will be reporting about the 4-dimensional 5-level pulse amplitude modulation, or the 4D-PAM5. So what is 4D-PAM5? It is a multi-level signaling scheme, and the 4D in it means that the data is sent over 4 wires at the same time. The 5 represents the 5 voltage levels. So how does it work? Each transmitted symbol represents one of 5 levels: -2, -1, 0, +1, and +2. 4 levels represent 2 bits, and the 5th level, which is 0, supports forward error correction, or FEC, in the form of 4-dimensional 8-trellis coding. This will be later on explained near the end of the report. The 4D-PAM5 line coding scheme uses 5 different signaling levels and transmits on all 4 wire pairs simultaneously. This achieves a baud rate of 125 megabauds per second on each channel and an overall baud rate of 500 megabauds per second. To make it easier to explain how this works, we will be comparing it to the MLT3 signaling. In the picture, you can see the comparison between a 100 base TX MLT3 versus a 1000 base T 4D-PAM5. The 4D-PAM5 has the same baud rate as MLT3, but the only difference is that it uses 5 signaling levels. Every symbol transmitted corresponds to 2 bits of data, so the gross bit rate is 1000 Mbps to 8 bits during each 8 nanosecond cycle. MLT3 transmits one signal symbol per clock cycle, although the use of 4B5B block coding with MLT3 means that each signal symbol only includes 4/5 of the data bits. 4D-PAM5 encodes 2 data bits per symbol on each channel, enabling the transmission of 8 data bits per clock cycle. The number of unique signaling patterns required to represent every possible 8-bit data word is 2 raised to h to 8, which means it's equal to 256. However, with 4 channels and 5 signaling levels to choose from, it is possible to generate 625 unique signal patterns. As a result, the 4D-PAM5 line coding scheme has considerable redundancy. MLT3 uses 2 wire pairs to achieve a full duplex 100 Mbps operation, while the 4D-PAM5 uses a single wire pair to achieve a full duplex operation at a gross bit rate of 250 Mbps. In other words, data is transmitted in both directions simultaneously over a single wire pair at a gross bit rate of 250 million bits per second. This two-way flow of traffic results in a huge amount of collisions on wire pairs, resulting in some extremely complex voltage patterns. If you refer to the picture, you'll be able to see what a 1000 base TX implements full duplex operation over 4 wire pairs looks like. In order to ensure that the transmitted signal can be correctly interpreted by the receiver, the input data is scrambled using pseudo-random values in order to spread the transmitted power as evenly as possible over the frequency spectrum. The output from the scrambler is encoded using a convolutional code, which is also sometimes called a trellis code since it looks like a garden trellis, which is essentially a special kind of block coding. The encoding process adds a redundant bit to the data to be transmitted so that the receiver can recover the data even if some errors are introduced during the transmission. This is known as forward error correction, or FEC. This is only possible because, as mentioned in the previous slides, with 4 channels and 5 signaling levels available, there are 625 possible signaling patterns. The code words used to represent the data are chosen by the trellis encoding process in order to minimize the possibility of a DC component developing in the transmitted signal, and to maximize the ability of the receiver to maintain synchronization and correctly decode the incoming signal. The complex electronic circuitry in each node that encodes outgoing signal and decodes the incoming signal on each wire pair is combined into a single hybrid encoder and decoder unit. As you can see in the picture, each end has a hybrid component which can either encode or decode. These hybrid units use an array of sophisticated signal processing techniques including pole shaping, echo cancellation, and adaptive equalization in order to counter the effects of noise, echo, and crosstalk, and to separate the incoming signals from the outgoing signals. This is the end of my report. So that is how the 4D-PAM5 works.